Welcome back, everyone, after the break. And the last speaker of the day is going to be Luca Mesiti with Towards Elementary to Toposes. Luca, take the stage.
Thank you very much. So first of all, I'd like to thank the organizers for the opportunity to give this talk. And today I'll talk about elementary two toposes, which don't really exist actually, but that's a bit the point of this talk. So the plan is to tell you some things that I know that I've developed during my PhD or that other people have done, and also some things that I don't know and that you can take as an invitation to work on them, like either together with me or by yourselves. I don't know. I think it's a very interesting subject, which will have also a lot of useful applications, and there's still a lot of work to be done here. And we can start with what is well known, which is one-dimensional elementary topos theory. There are many equivalent definitions of topos, of elementary topos. I like this one, which says that an elementary topos is a category that has finite limits, is Cartesian closed, and has a subobject classifier. And now, note that the first two conditions are quite mild. So all the work is being done by the subobject classifier. In some sense, it's the most important ingredient here, at least in my opinion. And it's very interesting, maybe a bit surprising or magical, how many properties can be deduced from this simple definition. And these include all for free, finite colimits, power objects that generalize the power set, locally Cartesian closedness, which means that every morphism is exponentiable, extensivity, which means that we have coproducts and they work well with pullbacks, regularity, which is that we have a good image factorizations, bar exactness, which means that internal equivalence relations behave well, and hating category, which means that we have an internal logic which is full first order intuitionistic logic. And the idea, which goes back to Lovier and Tierney, is that an elementary topos is like a universe of generalized sets. So a universe in which we can do most of classical mathematics, and the idea is that an elementary topos shares all these good properties with the category of sets, so that it almost behaves like the category of sets. And then what is hard is when we try to generalize this to dimension 2, is to understand if all these good properties are automatically generalized in the two-dimensional setting, or if maybe we should ask for them directly inside the definition, and so on. And set is the archetypal elementary topos, and its subobject classifier is given by the inclusion of true inside the set of true and false. And this is a universal subobject in the sense that every other subset can be written as a change of base of this universal one along a unique morphism into the set of true and false, which is given by characteristic functions. And from this, it's not hard to extract the definition of subobject classifier, which is a map from the terminal object into omega, which is to be interpreted as picking true inside the generalized, inside an object of generalized true values, such that for every x, this function that calculates pullbacks along the map tau gives a bijection with subobjects over x. And so now we would like to go to dimension 2. And so in my PhD, I focused on two-dimensional classifiers, the generalizations of subobject classifiers, because for me it was the starting point to look at. And the two category of categories should be the archetypal elementary topos, two topos. And CAD satisfies good properties. For example, is complete, co-complete, Cartesian closed, regular, and bar exact, all in the two-dimensional sense. But it doesn't fully satisfy other properties. Remember that we wanted the power objects in dimension 1, which generalize power set. And here what does the job could be categories of presheaves, but we can only consider categories of presheaves on a small category. So there's some limitation on these axioms that the cut satisfies. And also not all functors are exponentiable, so cut is not locally Cartesian closed because only Condorcet functors are exponentiable, which are functors which lift factorizations of morphisms. And what about the two-dimensional classifier? Well, first we need to understand what should replace subobjects in dimension 2. And Weber proposed to classify discrete opfiberations. The idea is that in set, we classify injective functions, which have as fibers either singletons or empty sets. And now we want to increase by 1 this dimension of the fibers in the sense of homotopy type theory. And so the idea is that fibers of the functors that we classify in cut should be general sets, and discrete opfibrations are the perfect notion that does this job. They're functors which are able to lift morphism uniquely to any given source above. And exactly as we can first understand injective functions and then extract from that a notion of monomorphism in a general category, we can do the same process and extract the notion of discrete opfibration in a 2 category starting from the one in cut. And what is nice is that cut does indeed have a nice classification of discrete opfibrations, which is given by the category of elements construction or Grothendieck construction. It takes a presheaf and turns it into a discrete opfibration over the base. And this exhibits an equivalence of categories, well, at least if we restrict ourselves to discrete opfibrations with small fibers. And this is in some sense a limitation which is quite close to the ones we had before. And so discrete opfibrations are playing the role of subobjects in dimension 2. And the category set is playing the role of the object of generalized truth values. So all sets will be generalized truth values in this setting, and this will allow for a more expressive internal logic in dimension 2. And now there are 2 equivalent ways to capture the category of elements construction in an abstract way, in a way that will tell us how to define 2-dimensional classifier. The first one is uses comma objects. I like this one a bit better. And so the category of elements construction can be represented as taking comma objects from the inclusion of the singleton inside all sets. And this is close to the logic point of view. We still have some inclusion of true inside an object of generalized truth values, and then all other maps that we want to classify are still expressed as some kind of finite limit along this inclusion of true inside the truth values. But every time we have a comma object, like by a general theorem, we can always first calculate a replacement of the map we started from. In this case, we are going to find the forgetful from pointed sets to set, and then we can just calculate pullbacks of it. And Mark Weber followed this approach below to give a 2-dimensional notion of classifier. And so he has this universal discrete opfibration, which in this case is the forgetful from pointed sets to set. And the classification is via pullbacks. But I thought that it's good to point out and remember when this universal discrete opfibration comes from calculating a comma object from a map that starts from the terminal object, because this is closer to the point of view of logic, and the notion will be better behaved like this. So I define these good 2 classifiers. The notion is dependent on a fixed property for discrete opfibration. This is trying to capture the fact that in cut, we are not able to classify all discrete opfiberations, but just those ones with small fibers. And the good to classifier is a morphism omega from the terminal object, which is still to be interpreted as picking true inside an object of generalized truth values, such that the functor that calculates comma objects from that morphism omega forms an equivalence of categories with all those discrete opfibrations satisfying the fixed property P. And what I did in my PhD thesis was to focus on this two-dimensional classifier, especially on these good ones. And I found that all my examples had good two classifiers rather than just those weaker ones that consider pullbacks. And I wanted to develop a method which made easier and quicker to prove that something is a two-dimensional classifier. And so I developed a theorem of reduction to dense generators of the whole theory of two-dimensional classifiers. And as a quick recall, the dense generator is a set of objects in a two category, or equivalently a fully faithful sub-two category, such that the restricted Yoneda embedding is fully faithful. And now the Yoneda embedding being fully faithful means that all categorical properties that we are interested in of an object can be captured by looking at all morphisms that land into that object. This is a bit the philosophy of category theory. And the point of the dense generator is that it actually suffices to look at just those morphisms that come from the dense generators. And these already capture everything we want to know of the objects. And equivalently, this means that every object of our two category is a nice colimit of a diagram that only uses the dense generators. And the archetypal example is given by representables that form a dense generator in two-dimensional pre-sheaves. And so this is the theorem of reduction to dense generators. So if we want to prove that something is a good two classifier, we should prove that for every object F in the two category, taking comma objects from omega gives an equivalence of categories. And this theorem is saying that we can actually just consider those Fs that are dense generators. And plus a certain operation of normalization, which means that we can put together well all these equivalences on dense generators. And the proof is constructive. And this diagram is showing the constructive proof. So we start from a discrete opfibration phi in the middle, and we want to classify it. And so as we have dense generator, we can build F as a nice colimit of those dense generators. Then we can consider the change of base of phi along the inclusions in the colimit. And we end up with this bunch of discrete opfibrations over dense generators that we know how to classify. And at this point, we can induce a map on the colimit. This as long as the maps below form a cocon, and the operation of normalization is speaking about this precisely. Now, I'd like to show you in a concrete example for this constructive proof. And we are going to look at the two category of categories. The singleton category is dense in cut. And so we can just look at the classification over one. And there the classification is trivial in the sense that we just have the functor that takes functors from one into set and calculates the image of the unique element of the singleton. And this is clearly an equivalence of categories. The operation of normalization is trivial. And so from just this observation that we have an equivalence over one, we immediately get automatically that the category of elements construction is fully faithful and that it classifies precisely all discrete opfibrations with small fibers. And moreover, we know this in a constructive way. So we start from discrete opfibration P here in the middle. Then we will consider these pullbacks, which are going to be just the fibers of P. And then we collect them together to induce the map on the colimit. So we find precisely what we know of the category of elements construction, but all from this trivial observation that over one, everything works well. And then another setting in which we can apply this theorem of reduction to dense generators is that of two-dimensional presheaves and of stacks. And this is important because two categories of stacks give the two-dimensional Grothendieck toposes, exactly as categories of sheaves give one-dimensional Grothendieck toposes. And indeed, the stack is like a bicategorical sheaf in which we are able to glue together compatible families of objects, but now the compatibility can just be up to isomorphisms. It's this isomorphism phi here. And yeah, just an idea of what the stack is. And so we can apply the theorem first to two-dimensional presheaves, and then we can restrict what we find to get a good two classifier in stacks as well. And for two-dimensional presheaves, representables form a dense generator, so we can just look at the classification of the representables. And here we find that the Yoneda lemma forces the construction of a good two classifier. It tells us to send C to the discrete opfibrations over the representables. And this doesn't work entirely because this omega is not going to be a pseudo-functor. It's not clear that it lands in small categories. So we need to do a replacement operation. And this is done thanks to an indexed version of the Grothendieck construction that I developed together with Elena Caviglia. And the point that we are interested in this talk is that we can change discrete opfibrations in two-dimensional presheaves over F with presheaves over a Grothendieck construction of F. And so in our case, we end up with considering this functor that sends C not to discrete opfibrations over representables, but rather to these presheaves over slices on C. And this is a good two classifier in two-dimensional presheaves that classifies all discrete opfibrations with small fibers. So it's good to have that two categories of two presheaves have a good two classifier. And then what I wanted to do was to restrict this to a good two classifier in two categories of stacks. And the idea is that we want to find a stack, this omega j, which is embedded into the good two classifier in two-dimensional presheaves, such that it makes two factorization arguments work. First of all, we want the map from one to the good two classifier. We want the entire good two classifier in two-dimensional presheaves to factor through the stack that we found. And then we want all the characteristic morphisms relative to the discrete opfibrations in stacks to factorize through this stack omega j. And I proved that with the general argument that if those two factorization arguments are satisfied, then we have a good two classifier in two categories of stacks. And what we find is that we need to restrict the presheaves over slice categories to the sheaves over slice categories. And this gives a good two classifier in the two category of stacks that classifies all discrete opfibrations with small fibers. And this also solves a problem posed by Hoffman and Stryker when attempting to lift Grothendieck universes to sheaves, because they tried to do something like this. And it didn't work for them because they said it doesn't give a sheaf. And what's happening here is that it gives a stack, which is a bicategorical version of a sheaf. And it is also a good two classifier in stacks. So right now we know that two categories of stacks have a good two classifier, which is good because two categories of stacks will be Grothendieck two-dimensional Grothendieck toposes, and we want them to be preeminent example of elementary toposes in dimension 2. And this theorem is telling us that at least they have a two-dimensional classifier. But then we can come back to the original question and ask ourselves, what else should we add to the definition of elementary two topos? Okay, we can take these two-dimensional classifiers, either the good two classifiers or the ones we just consider pullbacks. But then what else should we add? And Weber suggested to add a duality involution, which is something that in dimension 1 is just not there because it involves opposite that we don't see in sets. And this is generalizing having the opposite construction of the category. In general, it's a two-functor from k co to k, such that we have pseudo-natural equivalencies of categories between, these are bi-sided discrete fibrations. So it's basically asking that the opposite sends a discrete opfibration to a discrete fibration, and then something a bit more than that, which involves the product here and product on the other side. And in cut, taking the opposite, the usual opposite, gives a duality involution. And for presheaves and for stacks, one can consider the pointwise opposite. So, but just when we consider presheaves on a one category C, because what we can do is the following. We can consider F co here. If we want to calculate the opposite of a functor F from C op to cut, we can take F co and then compose with the opposite. This means taking the pointwise opposite. But we have as source this C co-op, which if C is a one category, is going to be isomorphic to C op, but it won't be true in general. So it's trickier for general two categories of two presheaves to find the duality involution. So I don't know, that there's still some work to do, for example, to understand whether duality involutions are something that we want or if we don't want them. And there's a work in progress with Francesco Dagnino, which is going to justify a bit these duality involutions from the point of view of relational doctrines, thinking about the internal logic of an elementary two topos that should be a two-dimensional logic. And then another thing that we can do for sure is studying Grothendieck two toposes. They should be the preeminent example of elementary two toposes, so we can study them and understanding which properties we should then ask to elementary two toposes, studying, for example, these two categories of stacks. And what I proved is that two categories of stacks have all flexible limits. This is given by the fact that the pseudo-categorical stacks have all bi-limits at least. And there is an argument that shows that at least flexible limits are here. And these are the limits that don't consider too many strict equalities. So equalizers are not here, in general pullbacks are not here, are not flexible, but comma objects are flexible limits, for example, because they are less strict. And the idea is that stacks satisfy a gluing condition up to equivalence of categories. So some limits will be just too strict for stacks. And we don't have pullbacks in general, but at least we have these pullbacks along discrete opfibrations, and we have all comma objects, terminal objects, and these are calculated in two-dimensional presheaves and dense pointwise. But then it looks like we shouldn't ask for all finite limits in the two-dimensional setting because text won't have all finite limits. Maybe we should just ask for flexible limits. So we should be careful in generalizing to dimension 2 elementary toposes because maybe we don't want full generalizations of the properties. Also in CAT, we saw many of those examples, like it's not locally Cartesian closed because only Condorcet functors are exponentiable and so on. And another thing to consider is that in dimension one, we have a nice fact, which is that the codomain of a subobject classifier is always an internal Hating algebra. And a two-dimensional version of this would be that the codomain of the two-dimensional classifier should always be an internal topos. And so I think this is also a good property that we should aim to have. And Weber has already shown that with some assumptions, the codomain of a two-dimensional classifier is always Cartesian closed in the internal meaning. But maybe we should add assumptions to elementary two toposes that allows for this to always be true, and maybe always the internal topos axiom to be true. And so yeah, that's basically everything I wanted to tell you. There are a lot of things that I still don't know, that the community doesn't know, but I think it's very interesting to study this. It's a nice way to merge the theory of vibrations with the topos theory. So I think it's interesting. And it may be applied a lot also to logic, finding a two-dimensional logic, for example, internal to any elementary two topos. And thank you very much for listening.
Thank you very much to Luca for the nice talk. Now we move to question time. Paul Taylor raised his hand. Paul, please take.
I wasn't intending to be the first. There's an aspect of the logic of one toposes. So you will be aware of this, having dealt with homotopy type theory and the type theorists, namely what they call impredicativity, which doesn't, so far as we're aware, lift to the two level. So this would be the usual example is if you have all joins in a poset, then it has a greatest element, whereas having all colimits in a category doesn't give you a terminal object. I wonder whether you and there's some, so the type theorists want to deprive other mathematicians of this rather useful result in the order theoretic case. I wonder whether you have any thoughts on this in two toposes.
I've not thought about this particularly yet, but a lot of times it happens that in dimension one, you could do like many more things. For example, in set, you can just take power sets of everything. You're still inside set.
Yes.
Not any worries. But for cat, we can only classify discrete opfiberations with small fibers. And a lot of these limitations happen. So maybe it's again one instance of this. I don't know. I've not really thought about that yet. Though.
I think it's a difficult question, and
Maybe,
it doesn't help that when you have conversations with type theorists, it's rather like when you meet religious nutters in the high street and they want to tell you you're a mortal sinner for using impredicative arguments, and it seems to be quite difficult to have a constructive discussion with on the topic.
Thank you, Paul. Do we have other questions? So Nathaniel.
Hello, thank you for the talk. In the one-dimensional setting, there are various ways to construct elementary toposes from existing ones. I was wondering whether you had any analogs for the good classifiers. So if you have some sort of limit preserving two comonads and you look at the coalgebras, do you get a good classifier if the base has one or something like this?
It's something I would really like to do in the future. I've thought about it. No results yet, but it's quite interesting that Mark Webber has a transport result of good to classifier along a fully faithful, along the errata joint. And I think there's a way maybe to use this result of Weber to reach some of those results to build elementary two toposes starting from other ones. But still a lot, I've not started this yet. It's something I'd really like to do in the future.
Thanks.
I agree it would be very useful to have those.
So maybe I will ask a question and then there is time for other questions actually. So concerning the idea that omega should be an internal topos, one way to try and prove it is to show that you have the correct Giraud property of the category instead of trying and constructing its subobject classifier, which is going to be harder, I think. And to show that it's complete, I think it's actually not very hard. To show that the colimits are lex, this is going to be harder, I think. Did you think a bit about this, and do you have in mind a strategy to try and prove something like that?
I haven't thought about this much yet, except for noticing that this codomain of the good to classifier in stacks really looks like an internal topos because it's considering sheaves on slices. So it's probably going to work, but I've still not had the chance to properly look at it. I agree that maybe it's better to look at Giraud's axiom for this. Also, I still don't know whether to expect elementary toposes or Grothendieck toposes in general. I don't know. Maybe elementary toposes, but
I mean, in the special case of a stack, I would
in this
expect.
special case, yes, they will probably
I
be
expect.
Grothendieck toposes, and so I can just look at Giraud's axiom. Yes.
Yeah, I mean, this is like the simple case. I wasn't thinking of the super general case because there the definition is still wobbly. So
Yeah. Then what one should try to do is to add sufficient axioms to the notion of elementary to topos, maybe to always ensure this. But yeah.
thank you. So we still have questions. Should I say Callum or Adrian?
Hey, firstly, thanks for the talk, Luca. It's very, very interesting. I just wanted to ask regarding, you said at a certain place that it was more appropriate to just consider the flexible limits, I think it was, or particular kinds of two categorical limits. Just wanted to see if you had anything more to say about why there's a specific class of limits that's being considered here, because suddenly pre-stacks will have all enriched limits. So.
That pre-stacks, yes, but when you consider stacks, and if you consider them satisfying gluing up to an equivalence of categories. So in the notion of stack, you have an equivalence of categories between these descent data and the image on an object. Then they won't have all finite limits. They won't have all pullbacks, or they won't have equalizers, for example, because they are too strict in comparison to these equivalence of categories that you want in stacks. Because here you're seeing the notion of stack.
Mm-hmm.
You need to find them here. even if you consider just strict two functors, if you are interested in this gluing of families that are compatible up to isomorphism, and you want to glue them into something global that only recovers the starting local ones up to isomorphism, then this is not working well with the strict limits. And what I proved is that at least they have all flexible limits, which are those limits which are essentially they are nice representatives, nice strict representatives of bicategorical limits, because you have all bi-limits and you also have these ones. But yeah, it's just that you won't be able to have all finite limits in two categories of stacks at least. But these are going to be the main examples, and so you should limit this.
Great, thanks.
But you could have said finite B limits, right?
Yeah, yes,
So you could have gone for finite B limit, and then it would be the finite you want for the correct notion of to limit that you want.
Yes. And just saying a finite strictly enriched limits are not going to work, but bi-limits seem to be working much better.
So we have still many questions. Let's go with Zurab first.
Thank you very much. I have two somewhat related questions that relates to our other discussions as well, Luca. So is it true or not that if you take an ordinary category and view it as a two category where two cells are equalities, then you, in that case you want to recover back the ordinary notion of a topos? And my second question is, what about the case where your two category is actually a poset enriched category? Can you, because things probably simplify in that case, do you have examples and do you know a bit more about this intermediate case? Thanks.
So for the first question, it's something that is not going to work like that. That is because we are upgrading subobjects to discrete opfibrations, and they are just different. It's not that the discrete opfibration is a generalized version of subobjects, like in a precise way. What I think might work is that if you take some reflection of a two category, then maybe you find the one-dimensional elementary topos. Or starting from one category, what you can do is taking internal categories into it, and maybe there's more chance to find an elementary two topos. So I think there will be some results like this, but they are not just viewing a one category as a locally discrete two category. You need to do something a bit more intricate. And for the second question, I've not thought about it yet. Maybe you are right. There's a lot of simplification, and it would shed more light on which other axioms we want to take for elementary two toposes.
Thanks.
So in the case of a topos, the way you extract a locale, you take subobjects of one. So in the case of a two topos, the way you extract a topos, you take discrete opfibration over the point. And this has to be a one topos inside it. And indeed, in set, discrete opfibrations over the point, in cat, discrete opfibrations over the point is set.
Yes. Thank you for this comment.
So we have, I think, John, and then Nathaniel, and then we finish.
Yeah, so there's a recent paper of Joseph Helfer called Internal One Topoi and Two Topoi, which add axioms to Mark Weber's definition sufficient to show that the discrete opfibration classifier is a one topos in two topos. So I think that's relevant and it's worth looking into paper.
Yes, thank you very much. I think I saw it like in the archive mailing list, and I put it in my reading list, but I've not looked at it yet. But it's probably going to be really relevant to what I've done.
Yep.
Thank you.
Then we have Nathaniel that closes the day.
I just wanted to follow up quickly on Adrian's question, and I was wondering, since the limits you care about are the ones that are well behaved bicategorically, whether the two category of stacks has semi-flexible limits in addition to just flexible limits, because as John and Richard Garner showed, these are the ones that behave like bilimits essentially.
I've just considered flexible limits for now, because for me it was like a lemma that I needed, and in particular I needed comma objects, terminal objects, and pullbacks along discrete opfiberations, all these ones, and they were all given by this flexible, but maybe yes, maybe they also have semi-flexible limits. Thank you for the suggestion. Yes.
Thanks.
Okay, we call it a day. So first we thank the speaker one last time. Thank you, Luca, for this very nice talk. And thank you everyone for coming to this Ithaca event. The next one is going to be in a month or so, but do check the webpage for more information. And thank you for tuning in, and see you next